LED is the abbreviation of light-emitting diode. It is a semiconductor device that emits light when an electric current is applied in the forward direction. It is normally encapsulated with a plastic cover, having higher resistance than glass. Free electrons move to recombine with holes. To explain this concept, we will see what the ions are. Here is a neutral atom illustrated. When an electron leaves the atom, it becomes a positive ion. The cleared place is named a hole. This hole causes the positive charge of the ion. Under specific conditions, this ion attracts other electrons. Now we will see a negative ion. An electron is accepted by a neutral atom. This additional electron turns the atom into a negative ion. Under specific conditions, the ion tends to release this electron. Several situations are possible. This additional electron of the negative ion can occupy a free place in another atom, as we can see on this animation. This electron can also be shared in many different kinds of links, but also even nothing can occur. LED diodes are manufactured with direct gap semiconductor materials. Two kinds of bands can be seen in semiconductor materials: conduction band and forbidden band. In the recombination process, electrons move from high energy levels to lower ones. In nature, we find three different types of materials: conductor, with practically no band gap; semiconductor, with an approximately forbidden band of 1 electron volt; an insulator with more than 3 or 4 electron volts of band gap. The energy scheme of the LED semiconductor materials shows at the top the conduction band and at the bottom the valence band. Within the conduction band, the electrons are in the majority, whereas within the valence band the holes are in the majority. Depending on the employed material during manufacturing, the LED emits with different frequencies. The wavelength of the light emitted, and therefore its color, depends on the band gap energy. Most of the LEDs are based on aluminium gallium arsenide. In pure aluminium gallium arsenide, all atoms make perfect links with themselves, which does not let free electrons create an electrical current. When material is doped, the charge balance is modified by adding electrons or holes. Doping is the process of intentionally introducing impurities into an extremely pure semiconductor. Two different doping mechanisms exist: N-doping and P-doping. N-doping is based on doping with a small quantity of donator atoms. In this manner, permitted energy states are realized closely below the conduction band. An extrinsic N-type semiconductor is created. The electrical current is mainly constituted by the flow of electrons. Electrons are the majority charge carrier. P-doping is based on doping with acceptors. Energy levels closely above the valence band are realized. Holes act as majority charge carrier. In reality, the only parts that move outside the atoms are the electrons, but these electrons produce a similar and simultaneous move of holes. By combining P-type and N-type semiconductors together, we form a P-N junction. In the P-doped side, holes constitute the majority charge carriers, represented by red walls. Electrons are represented by blue walls. In the N-doped side, the opposite occurs. After combining N and P-type zones, some of the free electrons in the N-doped region diffuse across the junction to the P-type side. As electrons diffuse, they leave positively charged ions on the N-doped side behind. Similarly, holes of the P-type part leave their atoms and these become negatively charged. Then, there is a separation of charges, causing an electric field. The electric field is opposite directed to the flow of diffusion currents. It increases in the same manner as ions are created up, to the point where no hole or electron move anymore. If the diode is connected in forward, the potential decreases. The depletion zone shrinks in size. Then electrons move to the transition zone, making themselves recombinations, and energy is free in packets of light. Photons. When the power supply terminals are reversed, the potential in the p-n junction increases. The electric field opposes with more force the diffusion process. No recombination takes place, and therefore no photons are produced.